Hi, I'm Veli from Greenwood Solutions. This week we're looking at DC cabling on a solid ground mount system, Part 3. After watching the presentation, you'll understand the pros and cons of a 4 or 6 mil cable approach on those runs, whether to parallel or not to parallel, and the cost benefits of one design over another. Now, if you like what you see, hit that subscription button. Let's get stuck into it. Ready, steady, go. In our last presentation, we looked at the DC cabling requirements of a solar ground mount system, so let's revisit the details. The size of the system was 1.28 megawatt. All strings consisted of 20 by 400 watt panels. There was 8 strings per row and 20 rows in total. In the case of the combined length of the positive and negative cables per row, it's approximately 256 metres. Each string's horizontal distance has been calculated at 10.65 metres approximately. The string is across 2 tiers, 10 panels per tier, takes into account the panel's width and the gaps between the individual panels. Distance from row 1 to row 20 is approximately 133 metres, and that's not including the perimeter access which you require in all ground mount systems, so 4 metres north and 4 metres south. There's 160 strings in total, all non-parallel, so all single strings, and each row requires 256 metres of DC cable. And then there is the runs to the inverter station, which is located behind row 20. The longest run, no parallel strings using 4 mil squared, had just under 3% on the volt drop, so pretty close to that recommended max. The longest run, 2 strings parallel, where we use 6 mil squared, the volt drop was still under 3%. And then we also could use 4 mil squared possibly on the internal cable runs within the string if combined V drop is less than 3%. So in this table you can see using 4 mil cable individual strings, it's about 27,000 metres. It was a little bit more. With 6 mil squared cable with parallel strings, so half the amount of strings, you're looking at about 16,000 metres of total cable length. And you can see the cable cost per metre for those two, 6 mil and 4 mil. And the total cable cost, 27,000 for the 4 mil individual strings and 24,000 for the 6 mil parallel strings. If you factor in also that when you're paralleling strings, you're using half the amount of DC isolators as a non-parallel situation, the savings add up. And if you also add in that there's less labour involved and less connections made, the costs difference starts becoming considerable. Now, we've made calculations in regards to 6 mil squared paralleling cables for the 1.28 megawatt project and have assumed the following. The internal cabling is all 6 mil squared. All the final runs from the centre of each row are in 6 mil squared. Volt drop and current carrying capacity of the 6 mil cable is satisfied. But there are more questions to ask. Now, can I use 4 mil squared within the rows on some rows that are closer to the end, in other words, closer to the inverter station? And what are the dangers of using 2 by different cables within the same row, i.e. using 4 mil squared from the string to the isolator and then 6 mil squared to the inverter station? At what point can I change to a 4 mil cable for the complete final run to the inverter station? So with the 4 mil all individual strings, no parallel strings, the highest V drop was on row 1 for that run of 166 metres, and it was 2.33%. Now the lowest volt drop for that final run is 0.46% at row 20. In fact, it's really only the 33 metre internal run with maybe a metre extra hitting the inverter station. So the average volt drop is 1.33%. So when we're looking at 6 mil squared, all parallel strings, right? The highest volt drop is row 1 for the string that's furthest away, and that's 2.8% using 6 mil for that 166 metre run. Now the lowest volt drop, obviously again, is row 20, and this time it's 0.31% for that 33 metre run. The average volt drop is 1.49%. Now remember, with the 6mm all parallel strings, we are actually carrying double the current on those parallel strings. We're not carrying 10 amps, we're carrying 20. Now 6mm squared and 4mm squared all parallel strings. So the highest volt drop row 1 is 2.8% for the 166 metre run. The lowest volt drop row 20 is 0.46% for that 33 metre run, and the average volt drop in this situation is 1.82%. We're using 6mm squared for the first 7 rows, but with the next 13 rows, we're using 4mm squared. So we've actually gone down from using 6mm squared for 13 rows. With this particular case study, I've looked at maintaining the volt drop to below 3%, which is a should, not a shall, but really, ideally, you'd probably want to look at maintaining all volt drops below 2%. Under cable used, you've got 4mm squared, and we know that's just for single strings, non-parallel. We've got 6mm squared, we know that's for paralleling 2 strings, and 4 and 6mm squared, we know that's for paralleling 2 strings as well. Now, the highest volt drop, we've gone through those before. The lowest volt drop, you can see in the 4 and 6mm squared category, it's slightly high because we're using 4mm on that last row. The average volt drop is a little bit higher using 4 and 6mm squared. The max current carried, obviously it's 10 amps because it's single string for 4mm squared, but 20 amps for both 6mm and 4 and 6mm squared because we're paralleling. Number of DC isolators, obviously 160, one per string for 4mm squared, and for the other 2 categories, 80. Now, total cable cost, and this is at $1 per metre for the 4mm and $1.50 per metre for the 6mm. $27,000 for 4mm. $24,000 approximately, $24,154 for 6mm only. Now, by changing some of the rows to 4mm when we parallel, the 4 and 6mm design is $20,173. So we've saved a tad over $4,000 by changing what cable we use. So you can see with a little bit of a design tweaking, we've saved $4,000 on cabling alone and still fallen well within the 3% DC volt drop that is recommended. One question that was asked is, can we use, say, 4mm strings within the row, coming to the center of the row, remember, and then 6mm runs? And the answer is we can do that, but I think it would be a little bit confusing for the actual installers if they have to remember that, oh, we're using 4mm within the row and then 6mm for that final run. It's best to go, you use the same cable within the row as you do on that final run. Conclusion, your design needs to take into consideration the different cable characteristics. Volt drop and current carrying capacity of the cables has to be considered, and significant savings can be made if using parallel strings. Thanks so much for watching our presentation on DC solar cabling on a ground mount system, part 3. I'm Valley from Greenwood Solutions. If you have any questions, any inquiries, any answers, please feel free to drop us a line. And if you like what you see, hit that subscription button. Bye for now.